So the first two questions tell us to multiply, so we're kind of going back to that just to kind of get an idea of the similarities and differences. Now, we've already touched on cases where the leading coefficient is not equal to 1, but this is to kind of formally address that. So if you're going to distribute, you're going to take each term of the first binomial, in this case binomials, and multiply it by each term of the second binomial. All right, and that would be the same process regardless of the nature of each binomial. All right, so they could be super complicated or they could be super simple. Either way, it's going to be the same approach. All right, it's just the result that's going to be a little different. All right, so x times x gives you the x squared. X times a 5 gives you a 5x. 3 times the x gives you a 3x, and 3 times 5 gives you the 15. All right, and so what we've been kind of working off of is the idea that when you have leading coefficient of 1 inside the two binomials, it kind of plays out this way where whatever the two factors are, or sorry, whatever the two numerical terms are, they correspond with the terms in the expansion that have a power of 1. All right, so the x terms basically. All right, and so when we would go to factor it, it would be like, all right, so what are two numbers that multiply to 15 that add to, in this case, it would be 8 if you simplify. So if we were going the other way, that's how we would think about it. Because those two numerical terms within the binomial would have to add to whatever the middle number is in the trinomial. All right, but when you expand out in number 2, we're looking at 2x squared plus 10x plus 3x plus 15. All right, so it's no longer the case that these two numbers are just simply whatever these two values were. It doesn't work that way. But there is a rationale to it. It kind of works out nicely. It's just in a little bit of a different way. Right? So these two values are not going to be the same as these two here. All right? But what those two values will be would be what we call the outer product and the inner product. All right. So if I were to multiply the outer two numbers, whatever the coefficients are, that'll give me one of those terms of the expansion. If I multiply the inner two coefficients, that'll give me the other term of the expansion. All right. So I'll have two terms of the expansion based off of those products. All right. So what that would look like, if I were to just kind of clean this up a little bit, I'll just pull this out for a sec. I'm going to duplicate this. Copy. Bring it down here. Bring this. Lasso tool required. If I were to take this term and this term, those two terms, and multiply just the coefficients. 2 times the 5 will give you a 10. So that'll give you the 10x that we're looking for. The 3 times a 1 will give you a 3. Bring the x along for the ride. That'll give you a 3x. Okay, that's not an arc. And these two numbers, the 3x and the 10x, are the two values that make up the expansion. Now, if I wanted to go the rest of the way and simplify this, I would get 2x squared plus 13x plus 15. All right. So if we want to go the other way, so as in going from the trinomial to the binomials multiplied, I'd be looking for two numbers, yes, that multiply to the c value, right? But I need my outer and inner products to add to the b value. All right. So, I mean, there's a whole process written below, but this is the simple gist of it. All right. So, we need two numbers that add to the C value. Oh, I'm sorry, that multiply to the C value. Where the outer and inner products add to the B value. Add all right. So if we look for factors in number 3, so let's try to factor the trinomial. Those directions probably could be a little bit better. I'll take it as a typo. Factor the trinomial. Could try to factor it. That implies that you're allowed to not be successful. I'd like you to be successful in factoring the trinomial with as many attempts as it takes to do so. All right. So we're looking for two numbers that multiply to 4. All right. So we make our list. You do this on paper or in your head, it doesn't matter. But if we're going to multiply to a positive 4, the possibilities are 1 and 4, -1, -4, or 2 and 2. Well, also -2, -2. All right. Now this is where the confusion comes in. Because if you're not aware of this relationship, you'd look at these possibilities and say, well wait, none of those pairs add to an 8. It's not the pairs that need to add to 8. It actually never was. Right? It was always the outer and inner products. Right? So we start with our framework, 2 sets of parentheses. Now we kind of neglected this because in this case the 3, that leading coefficient of 3, since it's prime, there's only so many ways that could play out. But we should actually also look for factors of the A term as well. All right. So because we need our first 2 entries to multiply to 3x squared. In this case, it wouldn't have been really too difficult because you think about how are you going to get to a 3x squared. Most likely 3x and x. Could also be -3x and -x. All right, so we'll just put the 3x and the x in here. For more complicated situations, you might find yourself making a list like this for the leading coefficient. All right. So now I'm going to just start placing values with the idea being that my outer and inner products need to add to whatever the middle number is. So these 2 values multiplied plus these 2 values multiplied need to add to whatever the middle number is. Poor quality box there, so let me just do that again. All right, so you try something. And if it doesn't work, you try something else. Now, experience tells me, and also a good dose of common sense, tells me that I'm going to just disregard the negatives here because there's nothing negative about my trinomial. It's entirely positive. Right? I don't see any negatives there. I don't see any minus signs, so there's no reason to think that a negative value would make sense. So now I just cut the possibilities in half. All right? So now I would look at this and say, all right, well, is it the 1 and 4 or the 2 and 2? Well, the 1 and 4 could actually go either way. So that's what makes things a little dicey here, because you have a 3x and an x. Depending on where you place the 1 and the 4, that'll give you a different outer and inner product. So for example, if I put the 1 here and the 4 here, 1 times x would give you a 1x. All right, 3 times 4 would give you a 12, so 12x. All All right. So that would give you the wrong sum, because when you add these two numbers together, you don't get 8x. All right. So aside from that being the wrong possible pairing, at least in this arrangement, you have to also consider that it could be the other way around. All right. It's not really aside from being the wrong possible, grammar. So I'd swap them, because if I put the 4 here and the 1 there, I would get 4x and 3x. Previously, I had a sum depending on same numbers, 4 and 1 versus 1 and 4, same numbers but different order. My outer and inner products are now different, which give me a different sum. In this case, 7x instead of the 13x. And it's still nowhere near what I need it to be. Well, actually, that's not true. It's very near, just not near enough. It needs to be precisely whatever that b term is. All right, so we've eliminated 4 and 1 or 1 and 4 as possible pairing. So now I would try 2 and 2. The benefit of something like 2 and 2 is there's only one arrangement that you could have. Even if I swapped the 2 and 2, it wouldn't change the outer and inner product. So a lot of folks will try that pairing first, because that's kind of killing two birds with one stone. All right, so put the 2 here, the 2 there, 2x, 6x, add them together, you get 8x. That means that these two would be positive, and now I have my factors. All right, it's very painstaking. There's other ways to do factoring by algorithms. Like if you use what's called the AC method, things like that. But this is the number sense approach, and it's the quickest and easiest way to do it. Requires the least amount of writing, but it takes a lot of practice to get to a point where you don't have to do the writing. The other methods will always involve writing, and it'll always involve 4 or 5 steps, which is why I kind of steer away from that. All right, so it's like you're working on your ability to factor, like numerical factors. You're working on your number sense, and you're also getting the trinomial factors completed more efficiently. All right, so I mean that's really what this little section below is really detailing. But it's not really giving you a procedure as much as it's just telling you what needs to be in place. All right, so let me do another example, or 2 or 4. I definitely want to get one with a negative leading coefficient in there, and one where the leading coefficient is a little funkier. All right, so we'll do number 3. We'll do 3, 7, and 12 together. All right. And just like I've been doing, I mean, maybe you don't know, because if you haven't gone to the YouTube channel, you probably haven't seen this, but I've been compiling videos from each class throughout the day. So I do 3 problems with you, I do 3 other problems with period 2, and 3 other problems with period 9. And so you have a nice sample of different solutions up online. So if you need another look at it later on, it's there for you. All right. So we're looking at factors of the A term, factors of the C term. All right. Usually the A term is relatively simple because it's either a 1, well, it's a 1 or something else. If it's a 1, it's very easy. If it's something else, it could be a prime number, in which case it's still pretty easy. It's when it's something that has multiple factors, like 16. 16, you can get to a 16 by 1 and 16, 2 and 8, 4 and 4, all right? Or negative versions of those things, all right? But technically, you should consider all the possible factors of the A term, 1 and 5, -1, -5, all right? And the C term, -4 is the C term. So 1, -4, -1, +4, 2, -2. You could also say -2, +2. it's just weird to think, maybe even like you don't believe me, that at some point you'll be able to do all this in your head. I mean, those of you who are there already, you do believe me, but if you're not seeing it yet, it's like, yeah, there's no way I'm ever going to be able to do this in my head. And one day it'll all click, and that's all you'll want to do. Just like, all right, let me just think about this for a second. Oh, it's this and that. All right. So I would start off with the most obvious pairing for the first two terms. If I'm going to get to a 5x squared, it could be the 1x and the 5x, or it could be the negative 1x and the negative 5x. The more likely possibility is that it's 1 and 5, or 5 and 1 if you want. But I'll do 1 and 5. 1x, 5x. It will work if you go with the negative 1, negative 5. All right? It's just the values that make up the rest of each binomial will be different. All right? But you'll still get an appropriate product. All right? So now what I'm going to do is place one of these factors, or one of these pairs, possible pairings. They're not really combinations anymore. I mean, I don't want to get into the world of probability and stuff like that, but they're called permutations. Anytime you talk about an arrangement of values, it's either an arrangement or a permutation. Fun fact of the day. So I would take a possible pairing that I think is more likely than not. All right, and so it's like, well, how do I know what's more likely? Well, I'm looking at a fairly large B term here. Let me get a different color. I'm going to go blue for those keeping score at home. All right, I'm looking at a fairly large B value, B term, which means that I need a fairly large product. All right, so I would be thinking, all right, if I got to multiply, if I got to use my rainbow, no, it's still not, rainbow is not a good name for it. My arc diagram, I'm just going to call it arc diagram from now on. If I'm going to use my arc diagram, knowing that I'm multiplying the inner terms and the outer terms, I would be thinking, all right, if I multiply 5 by the larger available number, that'll get me to a larger B value. All right? If I take the 5 and multiply it by the smaller of the two available numbers, it's not going to get me a larger B value. Right? So I'll show you the wrong combination first, permutation, and then you'll see what I'm talking about. So let's say I do the 1 here and the negative 4 here. All right? So the 5 times the 1 will give you a 5. The negative 1 times, the 1 times the negative 4 will give you a negative 4. All right? Those are two fairly small products. So if I add two fairly small products together, my result is going to be fairly small. So that's no good. But if I swap them around, I get something more reasonable. All right? Because 5 times 4 gives me 20. Now, it's the wrong sign, but it's stepping me in the right direction here. All right? So 1x times 1 will give me a 1x. Add these two numbers together, I would get negative 19. It's the exact opposite of what I want. But I do know I'm onto something here, because if this 20, instead of being negative, if it were positive, and this one was negative, that would get me where I wanted to go. So that's just telling me that this negative should be associated with this term. So it's really telling me that my winning pair would be negative 1, 4. Negative 1, positive 4. So x plus 4, 5x minus 1. But again, we don't necessarily know the order it's supposed to be in until we do our arc diagram. Arc diagram. Yeah, that's what we're going to call it. Okay. So it takes a little doing, and definitely patience, but This is the quickest avenue to being able to do this stuff in your head. All right. So let's take a look at number 7. So again, I'm looking at factors of my first term. All right, so I have the -2. Factors are -1 and 2, well, I'll just write 1 and -2, because -2 and 1, same deal. All right, now fortunately, my C term is the same thing. So its list of factors will be the same. So we get into the arc diagram. I wish I had a wider palette, like 4 colors at least. All right, I gotta get my framework. My first 2 terms have to multiply to -2x. All right, so it's a question of, all right, well, which one's the winner? Who knows? You got to make a choice. So you try -1 and 2. All right. So then we're going to place a value in each one of these binomials, hoping that our arc diagram is going to play out the right way. As in, we're going to get our products, the outer and inner product, and the sum of those products will be whatever the B term is. All right. So you think about, okay, how can I get to a 5? Well, my possible values are 1 and 2. One's positive, one's negative. I mean, that's important, but not as important in the early going. You think about how you can get to a 5. If I had a 4 and a 1, that would be great. I don't have a 4. If I had a 2 and a 3, that would be great. I don't see how I'm going to get a 3. I'm just thinking about different ways to add to a 5. 4 and 1 would be great. Right? So, okay, well, I do have a 2 and a 1. And if I multiply the 2 by the 2x, that'll get me a 4x. If I multiply the 1 by the -1, that'll get me a -1. And you're like, dang it, that's going in the wrong direction. All right, so then you'd say, all right, well, hold on. What if this -1 were a positive 1? That would do the trick, right? So this negative here is screwing everything up. So it's like, well, how can I make it so that this becomes, through multiplication, a positive 1x? Well, if this is a -1x, I'd have to multiply it by a -1 to get a positive 1x as a result. All right, the 2 times the 2x will give me the 4x. I'm good there. So now I have my pairing. So knowing that it was 2 and 1 got me through the door. All right, assigning the appropriate signage, plus or minus, came through the arc diagram evaluation. All right, so now I have 2 factors, -x plus 2 and 2x minus 1, and they check out. All right, the outer and inner products add to 5x. The first 2 terms multiply to -2x squared, which was what we needed. The last 2 terms multiply to -2x, also what we needed. So we're good, we have it. All right. In a lot of ways, this is really covering properties and relationships associated with math, just like number sense and understanding integers and things like that. There's a lot of stuff going on here. Worst case scenario, it's a whole lot of trial and error. Right? We don't really want that to happen, but we're okay with it happening early on, as long as you're working towards understanding why the placement of the numbers is so important. Right? So, and don't get thrown off by things like in number 9, where there's a y instead of an x. You treat it the same way. All right. right, so I wanted to do number 12. All right, so again, we're looking for factors of the first term, factors of the last term. The only difference here is the sign. So to get to a 6, we could do 1 times 6. It could be also 6 times 1. The order is important. All right. It could also be -1 times -6, 2 by 3, -2 by -3, and everything in the reverse order is also possible. All right. Then we have a -6. All right. So same deal, except the signs are going to be different. All right. Not just different from like what we just wrote, but different from each other. So one's going to be positive and the other's going to be negative. So 1 -6, -1 +6. 2 -3, -2 +3. All these possible pairings, they make things interesting. Let's put it that way. All right, so we know we're going to have an x and an x. I'm going to just start hanging on to this. All right, so we just kind of have to go for it. You know, like, is it going to be 1 and 6, -1, -6? I mean, more likely it's going to be positive, but you don't really know. Right, so 1 and 6 or 2 and 3, just take a stab and see how it goes. Right, if it doesn't work out, then you find yourself going with the other possible pairing. So I'll start off with the 1 and 6. I'm going to go with our arc diagram. All right, and so again, just taking a shot in the dark. I need to get a 5 out of this somehow. Well, 6 minus 1 would be 5. That would be beautiful. I mean, if I could get that to work, that'd be great. So maybe I do have 6s and 1s here to work with. So if I try doing that, though, you know, let's say I tried putting the 1 here and the 6 here. All right, 1 times 6 will give you a 6x, but you'll also get another 6x here. That's not going to get you near a 5. All right. No matter what you do with these two terms, you're not going to get near a 5. Because if they're both positive, that'll get you as high as 12. If they're both negative, that'll get you as low as -12. If they have different signs, that'll get you to a 0. So there's no way that this is going to play out the right way. All right. So then maybe you try 2 and 3. All right, so 2 and -3 and so on. Oh, and just to be clear, I didn't even consider putting the 6 here and the 1 there, all right, because 6 times 6 is 36. That's going to be way, way too far away. All right, so I'll try 2 and 3. Gives me a 12 and a 3. All right, so just a more shorthand way of writing it. So, oh, that doesn't work. Switch them around, because even if you change 1 to positive, 1 to negative, you're not getting to a 5 using these two numbers. All right, that's why I say it's not as important that you worry about the signs until after you get the numerical values down. You have to look at the two numbers and say, can I get a 5 out of these two through addition or subtraction? The answer is no. So you swap them around. 6 times 3 is 18. There's no way. All right, so you get 18, a 2, adding them, subtracting them in any possible ordering. There's no way you're getting a 5 out of that. All right. So after I've gone through every possible arrangement of these values based off of 1 and 6, now I can conclude that 1 and 6 was not the correct possible pairing for the leading terms. So I'll try 2 and 3. I want to go red. All right, and if you go through every possible pairing in every possible way and it doesn't work out, it means one of two things. It means you made a mistake somewhere. You didn't consider a possible pairing, and because of that, you got to do the whole thing all over again, which is terrible. Or it's not factorable. All right, so looking at the 2 and 3 as my leading coefficients for the binomials, and making the assumption that those are positive kind of leads me in a particular direction. Like, for example, I'm not going to look at this as being 6, right? Because that's going to get me an 18, and again, that's going to get me too far away from the 5. All right. So if anything, if I'm looking at these possible pairings to get to a -6 through a product, I would put the 1 here and the 6 here. All right. But still, same issue we had before. We have 3x, 12x. Through addition, subtraction, there's no way you're getting to a 5 from that. All right. Then I would look at these. All right. Now this is where the number sense comes in, because there's no circumstance in which I would put a 2 here. All right. I would not put a 2 there. I wouldn't even consider it. And in fact, that would have, if you really think about this, that would have eliminated, sorry, I can't even speak, 1 and 6 from any possible contention here. Because if this is a 2, that means that there's a GCF here. If there's a GCF here, there should have been a GCF here, but there wasn't. So you can't be looking at any possible factors that would create a GCF based off placement of numerical values, right? That's kind of advanced reasoning. It takes a little while to get there. For now, it's just trial and error. But if you start thinking that way, it really streamlines how many possibilities you would have, right? So if I'm doing this on my own, for my own purposes, I would have never even looked at these possibilities, right? Because no matter where I put a 1 and a 6, it would have created a GCF. And since the original trinomial didn't have a GCF, those could not be possible. The only possible arrangement of 2 and 3 that would work and not create a GCF would be 3 and 2. All right, 9x, 4x. So I'd be looking at, okay, 9x and 4x. How am I going to get from a 9x and a 4x to a 5x? Well, if I subtract the 4x from the 9x, that'll get me there, which means that this term should be negative and this one should be positive. Right? That's easily the most challenging type of situation, right? Aside from like the trick questions, like going back to number 9. Number 9 had a GCF in it. If you factor out the GCF, it's much simpler, right? So it's kind of a trick question in that regard. But this one's the juiciest one. It takes a lot of patience, all right? But once you really start kind of resonating with this material, it all starts making sense, right? Which is why we spend so much time practicing this stuff. Term, my 2x squared. I'm going to get my framework in here. My 2x squared, coefficient of 2. 2 has factors of 1 and 2. -1, -2. Then I also have my c value with factors, well, it's -1, so there's only so many ways that that's going to work. It could be 1, -1, or -1, +1. All right. To get to the 2x squared, the more likely possible combination would be 1 and 2, but the order may matter, but we'll just go for it. 1 here, 2 there. If I put the 2 first and then the 1, I'd still get the right answer. It would just impact what the other 2 terms are. Same deal with the -1, -2. If I accidentally put a -1, -2, I'd still get the right answer. It would just impact what values went in the remaining spaces in the binomials. All right? So you really can't go wrong with that. The only time it becomes trickier is if there are other combinations for the leading coefficient. Like, for example, the number 12. Like, you can get to a 12 with a 1 and 12, a 2 and 6, a 3 and 4. All right? In that case, it gets a little dicier. But if it's just the one possible combination, whether it's the 1 that comes first or the 2 that comes first, whether they're both positive or both negative, that's not going to make a difference in terms of the final answer, in terms of how you go about getting the final answer. All right, so then I create my arcs. That is not a good looking diagram. And now I just start placing values from my my red set here. All right, so I'll try 1 and -1. All right, so inner product 2x, outer product -1x. If I add these two together, I would get a positive 1x. All right, so I want a -1x because you see right here, right in front of that x, there's an understood 1. That's the same as saying -1x because the minus sign with the 1, -1. All right, what I just got here is a positive 1. If I add these two together, I get a positive 1. That's the exact opposite of what I want. Okay. So let's take the exact opposite of each of these factors, or products anyway. So let's say that this is -2x and positive 1x. -2x plus 1x, that would get the job done. So in order for this to have resulted from these two multipliers, one of them would have had to have been negative. All right, the 2x is fixed. We already established that that's going to be a positive 2x. So then it must mean that this is my negative. All right. In order for the 1x to result from the product of 1x and 1, that 1 over here must have been positive. And now we have our factors. All right, so it's just a little bit of manipulation of signs, but it's really nothing more than that. All right, once you have the numerical values, it's just a question of figuring out which one's positive and which one's negative. Now, this is a relatively easy one because the only possible numerical values for the coefficients were 1 and 2 and then 1 and 1. It's just a question of which one's positive, which one's negative. It gets a little dicier when you have a leading coefficient like 4. All right. So looking at a coefficient of 4, we have possible factors of 1 and 4, -1, -4, 2 and 2, -2, -2. And then for the 10, possible factors of 1 and 10, -1, -10, 2 and 5, -2, -5. So now we got to make a choice. All right, so is it going to be the 1 and the 4, or is it going to be the 2 and 2? And it will make a difference which one you choose. Because if you choose poorly, then you're not going to get the right answer, and you're going to have to go back and try everything with the other possible combination. All right, so give it a shot. We'll go with the, I always like to go with the repeated values first. It's just a choice. All right, so it's more like a habit. In this case, I'll show you that it's not going to work, but you know, you got to start somewhere. All right, so I'll put the 2 and the 2 here. Draw my arc diagram. I'm looking for an outer and inner product that would get me to a -13. Well, first we'll worry about getting to a 13, but then we'll worry about the signs after that. All right, so I could have a 1 and a 10 or a 2 and a 5, and because these two terms have the same coefficient, it won't matter which position they're in. That's why I like to go with the double value first. Like a 2, 2. If I put a 1 here and a 10 here, that's no different than putting the 10 here and the 1 over there. It's still the same two sets of terms, just in a different order. All right, so it really doesn't matter, which is, again, why I like to do that. All right, but this is a poor choice because the outer product's going to get me to a 20. The inner product's going to get me to a 2. There's another reason why it's a poor choice. I'll get to that in a second. But if you look at these two possible products, you would be looking to see if there's any way that you could add or subtract them in such a way that you would get a negative 13. There's no possible way I can add or subtract a 2 and a 20 and get a 13 as a result. If I add them together, I'll get a 22. If I subtract the 20 from the 2, I'll get a negative 18. If I do it the other way around, I'll get a positive 18. If they're both negative and I add them together, I'll get a negative 22. I'll never get a negative 13 out of it. All right? So this isn't right, but I knew that even before I got my outer and inner products. And the reason I knew that is because, and let me just get rid of this, it had to do with these two terms. If these were the two terms, if these numerical values were the actual coefficients, that would introduce a GCF. All right, we'd have a GCF in one of our factors. Now, that may not seem like a big deal, but if you have a GCF in one of your factors, that means that your original expression has a GCF. This original expression does not have a GCF. So if I create a set of factors in which there is a GCF, then I'm introducing something that shouldn't be there. All right. If the original expression does not have a GCF, then none of the factors will have a GCF either. Right? So I knew going in that 2 and 2 wasn't going to work because no matter how I placed these other values here, it was always going to introduce a GCF. All right? So I put in the 1 and the 10. I get a GCF here. That's no good. If I put in the 2 and the 5, I get GCF here in this expression. If I switch the 2 and the 5, I'd just get the GCF in the other expression. It wouldn't make a difference. All right? So before I even get started on a problem like this, I check for things like that. All right? And so what I would do is I'd look and see, all right, if I put a 2 and a 2 in here, will I have a GCF with these other factors? If the answer is yes, then I don't go with the 2 and 2. So then the only possible pairing would be the 1 and the 4. So I'd put a 1 and a 4 in there, and so I'd run into an issue in that regard also. All right, because no matter where I put the pairing of 1 and 4, I'm always going to get a GCF out of it. All right, so let's say I put the 1 here and the 4 there. All right. Oh, I'm sorry. What am I doing? I got to put the 1 and 4 here and here. 1 and 4. All right. So now I would put the 1 and 10 in. It's just I got to be thinking about, is there a way in which I could put the 1 and 10 in where I won't create a GCF? Same thing with the 2 or 5. All right. So if I put the 1 and 10 here, I'm creating a GCF. So that wouldn't work. But if I do it the other way around, I'm going to get an inner product of 40x. 40x and 1x, combining those, no matter what way you do it, you're never getting a 13 out of that. All right, so that's not going to work. So then the only possible pairing, if you kind of go through it analytically, the only possible pairing would be the 2 and the 5. It's just a question of ordering. All right, and it takes a little getting used to, but once you do, it all starts to come together. All right, so for example, if I put the 5 here and the 2 there, that's not going to work on a bunch of different levels. But the one I've been talking about is the idea of a GCF. There would be a GCF in this expression, and that would be a problem. All right. Also, 5 times 4 would give you a 20. 1 times 2 would give you a 2. You're not getting to a 13 that way. All right. So then the only other possible arrangement would be the 2 here and the 5 there. You'd have an 8 and a 5. If you take a positive 8 and add to it a 5, you're going to get a positive 13. I want a negative 13. So the way I would handle that is negating both of them, because negative 8 plus negative 5 is negative 13. To get a product of negative 8, this must have been negative. To get a product of negative 5, this must have been negative. And so those would be our factors. All right. So it definitely streamlines the process significantly if you're able to recognize those little things like a GCF or a lack of a GCF. All right. So one more, number 11. So again, we need to get to a product of 4. So actually, I don't want to just do a copy paste there. Actually, I can do it this way. Get this in, then do the copy paste. It's not necessarily going to be the 1 and 4, so let me get that out of there. Then for the 9, it could be 1 and 9, it could be 3 and 3, positive, negatives, a lot of stuff going on there. So for the 9, again, 1 and 9, negative 1, negative 9, 3 and 3, negative 3, negative 3. All right. So again, I mentioned this before. I like to go with the repeats first, all right, where possible. So I would be looking at this as my first, like if I'm just taking a stab at it, I have no idea. I'm taking the 2 and the 2 and the 3 and the 3 and seeing how that shakes out. All right. If it shakes out nicely, then maybe we get lucky and we don't have a lot of work to do. All right. So if I put the 2 and 2 here, the 3 and 3 here, we check our products, we get 6x, 6x. I need a negative 12x. All right, well, 6x and 6x will give me a 12x positive. I need them to be negative. So let's make them negative. All right, can't just make it negative, like just for the heck of it. It must have came through the operation of multiplication. If that's the case, then this must have been negative, because negative 3 times 2 will give you negative 6. This must have been negative, so 2 times negative 3 will give you a negative 6, and now you have your factors. All right, and just a side note, this could also be written as 2x minus 3 squared. All right, so I'll write same as. All right. Again, it's kind of tricky because my very first combinations, my very first selection worked. What if it didn't? All right, so then I would know that maybe 3, 3 doesn't work. So then I would move on to 1, 9. If that didn't work, then I'd say, okay, well, I guess 2, 2 doesn't work. All right. But I also looked at, now I didn't mention it because it was irrelevant, but I took a quick glance at my factors 2, 2 and compared them to the factors of 9. And since all of the factors of 9 are odd, there was never going to be a GCF between my set of factors for 4 and my set of factors of 9. So I didn't have to worry about, all right, well, is it possible that this combination won't work and I'm going to accidentally try it anyway and waste my time? It wasn't going to be like that. All right. So let me stop at the leading coefficient and its factors, 1 and 3, negative 1, negative 3. We look at the C value and its factors. All right. So negative 8, there's a bunch of different possibilities there. It could be 1 and negative 8. It could be negative 1 and positive 8. It could be 2 and negative 4. It could be negative 2 and positive 4. Or we could flip them around. Negative 8, 1, 8, negative 1. So that's a possibility that we got to be mindful of. All right. So now I create my framework, which is two sets of parentheses with x's built in. We're going to be looking for the arc diagram as part of this process. I'm just going to draw it now. And I'm going to save this. All right, so I'm going to pop in a 1 and a 3. So I'm going to assume that this is the correct arrangement for the x's. I mean, it could be the other way around. They could both be negative, but this is where I'm going to start. All right, now I need these products, the outer product and the inner product, to give a result of negative 2x. So that's what I'm going for. All right, so you just start with something that you think makes sense. All right, like for example, I would not put a negative 8 here. If I have a choice, I have a 1 and negative 8. I wouldn't put the negative 8 there and the 1 there, because negative 8 times 3 is going to give me negative 24. That's very far away from negative 2. All right, so we're looking for small products. All right, so we don't want anything to get out of hand too quickly. So I'd start off putting the 1 here and the negative 8 there. All right, so my outer product is negative 8, and my inner product is 3. Well, negative 8x, 3x. That's going to get me a negative 5x. Close, but not close enough. All right, and we know enough not to change it around and put the negative 8 first. I mean, it could be a matter of signage, but that's only going to impact, it's not going to impact the numerical value, just impact the sign of the numerical value. So let's say, for example, in this case, I took this negative and put it over here and went with a positive over here. Then I'd be looking at negative 3 and positive 8. It's still not going to give me a negative 2. All right, if the possible pairing that you come up with give you a particular number, the best you can do if you change the signs would be to change the sign of that sum. So that's not helpful. Not always, anyway. So then I'd move on to 2 and negative 4. So I'll try the 2 here, negative 4 there. 2 times 3 is 6. 1 times 4, negative 4. It's the correct it's the correct absolute. 6x minus 4x is 2x. It's just the wrong sign. All right? So if I want this to work out, I would need this one to be the negative and this one to be the positive. So you think about this pairing here and how you would get a result of negative 6x there. You'd get it by making this a negative 2. If I want this pairing to give a positive 4x, that would only happen if this were a positive 4. And so there's the factors. We got it. I mean, it takes a little patience. I mean, a lot of patience. Let's do another. Number 9 is kind of a trick question. I mean, it's more than kind of, it definitely is. It doesn't require this approach because there's a GCF there. I might as well show you. I'll just kind of leave that up on the screen there for a sec. So looking at number 9, you see here we have a common factor. Every one of these numbers is divisible by 3. So that would make my GCF equal to 3. So we would divide each term by 3. Now I can zoom in. Hang on to the 3, which would give me y squared minus 2y minus 8. And now I'm going to look at this trinomial as if it's its own problem. All right? So that it's new problem. So what do we do? The same thing we did before, except we don't have to worry about the leading coefficient, which is kind of nice. All right, so we'd be looking at, instead of x's, we'd be looking at y's, but it would have to be 1 and 1 as the leading coefficient because it's a 1y squared. But that -8 is going to have some factors. -1, +8, 1, -8, -2, +4, 2, -4. Right? And it's just a question of arrangement. Right? So I'm actually just using the same approach. So I'd go through my possibilities, looking for an outer and inner product. You know, if I put in the -1 and +8, you see what happens. You get a -1y and an 8y. That doesn't get you a 2y. All right, I need a 2y, a -2y specifically, as a result. All right, that's not going to happen here. All right, I could change the signs. I could change the order. The order is not going to make a difference here because the leading coefficients are the same. I could change the signs, but that's the only thing that's going to do is make this positive and this negative. It's going to make it a 7y instead of a -7y. I'm sorry, -7y instead of a +7y. So no help there. So we know it's not these two possibilities. So then we try the -2, +4. So we're looking at -2y, +4y. That'll give you a +2y as a result. It's the exact opposite of what we want, so we change the signs. We flip the signs around. And so we get a -2y. All right, and so as long as we remember to bring the 3 along for the ride, we have our factor form. And that's really it. I mean, it's I'd say it's probably tedious more than anything else, just going through the process. But the more experience you get, the easier it gets, which is why we're doing a lot of practice with this stuff. All right, we'll do one more, and then I'll let you practice on your own, or in groups, you know, the way we've been doing. I'm going to do something a little spicier, though. So on the next page, trying to remember which ones I did with the other class. Actually, I think I did all 3 of these problems. Actually, go 2 pages down the line. On page 27, let's grab number 4. All right, so looking for the factors of 4. That's 1 and 4, -1, -4, 2 and 2, -2, -2. We're looking for factors of 7, 1 and 7, -1, -7. Hit the wrong thing. Get my framework in there. So I have to make my first decision here. Am I going to go with 1, 4 or 2 and 2? Yeah. It's tricky. How do you know? You don't. You just take a stab at it and see where it gets you. All right. I always like to go with the double digit first, though. I mentioned that before. The reason why, and you'll see it in a sec, but the reason why is when I put the 1 and 7 in here, I won't have to worry about switching the order around. All right? Because if I have a 1 and 7 this way, you see I'd have a 2x and a 1, 2x and a 7, versus if I put the 7 over here and the 1 over here, I still have the same 2 expressions. It's just they've been flip-flopped. All right? If these 2 coefficients are different, then it does matter where I put the 7 and where I put the 1. All right? So It's just an easier way to get started if you go with the double digits first. All right. So you kind of prepare for the worst and hope for the best. So 2x times 1 is 2x. 2x times 7 is 14. So 14x. Unfortunately, there's no arrangement here, whether it's positive or negative, that'll get an 11x from a 14x and a 2x. If you add them together, the highest you'll get is 16x. If you subtract, if they're both negatives and you add them, you'll get a negative 16x. 2 minus 14 will give you negative 12x. 14 minus 2 will give you a positive 12x. Never going to get an 11x. All right, so that eliminates the 2 from contention. Since 1 and 7 is my only possible pairing for the factors of 7, I'm stuck with these two numbers. This one and this one. They're not going anywhere. All right. The fact that this whole scenario didn't work out means that the 2 and the 2 were the problem. All right. So these are out. So now we try 1x and 4x. All right. So 1 times 4 is 4, so 4x. 1 times 7, 7, so 7x. If you add these two numbers together, you're going to get an 11. All right? But only if they're positive, which means that these two factors have to be positive. So now I know my two factors are 1x plus 1, or just x plus 1, and 4x plus 7. I can get rid of this because it's straight now. All right.